Okay, hi. Yeah, Daniel asked how's the event. So it was pretty good. It was a good meeting. Uh, um, I don't know, it was pretty busy. Like we had a bunch of posters and talks and things, so it went pretty good. I mean, it was virtual, so it was kind of strange, but it worked out okay. Let's see. Anyway, yeah, I wanted to go through the quiz from last week. Just here. Let's see. Should be posted here now. Yeah, that's the quiz. This paper up. Paper should be here too. So it's a kind of interest. I mean, well, one of the authors on this paper was my grad student, and now she's in China at the Hanchu is at China at this spallation neutron source near Hong Kong. And these other people, so Bouet, actually I chaired a session and Bouet was the invited speaker at the APS meeting. And then Charles Hahn headed the polymer division of the National Institute of Standards in Washington, and then he moved back to China, and he's at the I think he's retired now more or less, but he's at the Institute of Physics or something. He's someplace like where is he? China Spallation Sources, where Henshu is. Oh, that's acknowledgements here. On this key laboratory, whatever, blah, blah, blah. So I think that's the top place as far as I know. I don't know much about China, the schools there, but basically some top place. So it's kind of it's a good group of people on this paper. I don't know the other people. Anyway, they're looking at just conducting polymers. So these are generally, so you see it goes double bond, single bond, double bond, single bond, double bond. So some pathway through the chain where you can find double singles. That's conjugated. It means that these have isomers, so the double bond can flip over to here or can flip back to there. So you can think of the kind of the extra electron, and the pi bond can just flip, kind of jump through this thing. Especially if you can provide an extra electron by doping it. So if you can put in something that dopes the chain to provide an extra electron, then it'll conduct, right? So you can conduct along that backbone chain. And that was conducting polymers was developed in kind of the late 90s, early 2000s. And then the problem with this is that all these double bonds are planar. So the way this is drawn is exactly how this structure is. It's a sheet. And that means it's rigid, like super rigid. So anytime you have like a double bond, so this thing is like 2D. And it's fixed that way. So if I put another one here, right, then that's all one sheet. And if I put another one here, that's the whole thing becomes just flat, smushed down, just the way you see it, except that these methyl groups at the end can spin around. That bond can spin, this can spin. So these side groups can spin around. So that means that if you tag on side groups, you can make this thing soluble. Otherwise, it's insoluble. There's no conformational entropy at all. It's completely rigid, right? So that means you can't do something like injection mold something with this, or extrude a fiber. If you wanted to make a polymer wire, you couldn't do it with this. You can do it if you put it into some strong acid sometimes, and then you can get this thing to extrude if it's dilute. right? So it's possible to do some processing with it, but basically almost impossible. In the original polythiophene, like this group, you had to produce electrochemically synthesize it, and then you could never process it after that. So you just made it in place and make a film, and then you could use it that way. So it has found some applications, but kind of limited because of this problem with the rigidity of the structure, right? But so the game of this conducting polymers is to try to find things that would be soluble. So you tag on different side groups to make it go into solution, and you get to these exotic molecules, right? So this is DPP, DTT, which probably nobody knows what it stands for. See, they don't even give the chemical name for that. They just say donor acceptor polymer. And this can go into chloroform at high temperature, or chloroform at room temperature, and then dichlorobenzene at elevated temperatures. So you can get a phase separation in dichlorobenzene. And the point is to look at this aggregation, what happens to this. So you expect these rigid chains then will kind of line up, right? And then form some kind of a fiber or something like that. That's their model. That's kind of what they're expecting. So this data shows that. So they have rigid chain. Power 1 means only one thing. It says log intensity log Q. Power 1 means it's a rod. There's only one answer to power 1. And then at the high end, this thing takes a dive. It just zips down. So that the slope out there, like in this case, or in the case of that other plot, which is like 8, I think. Yeah, 8. So if you measure the slope, it's about 4. In other words, if you take 1, 2, 3, 4 decades and then draw a line down, then you get something like 4 for the slope. So these are actually solid objects. These aren't like Kuhn lengths or persistence lengths. Right? This isn't a linear primary structure. The linear structure is over here, and this thing is 3-dimensional. Right? So somehow you have something that's 3-dimensional, which I guess, well, it's hard to say what it is. Basically, it's kind of like this planar thing, maybe stacked up. So at these size scales, at the 10 angstrom size scale, those things look like they're solid, and you can see a surface. So from that slope, you get a surface to volume ratio for this thing. Then this is the ratio. So this is a Guinier knee for that solid object, and those solid objects build up into a 1-dimensional for the bottom red curve. So that's slope 1. And then when you go to pour solvents, heat it up, and it phase, or you cool it down and it phase separates. So it's a UCST. So this is like temperature, composition, and it's going to be something like that. So it's 2-phase. So it's a normal like 2-phase system. So it's an upper critical solution temperature, right? Versus a normal polymer thing would be like that, lower critical solution temperature. Phase separates on heating, right? So anyway, the kind of phase separation that it does is it turns into it agglomerates. So you have rods, and then this thing isn't a slope of 4, so it's not a solid object it's making. It's something with a lower dimension, and that dimension is about like 2. So if you take 2 decades, here and go 1 decade here, the slope over here is about 2. So that means that this the molecule is planar, and somehow it forms sheets. And sheets with almost like a solid surface, because they have this power 4 out here at this end. Right, so you're going from linear, rigid chains, and then it agglomerates into these sheets. So it's kind of interesting what's going on with this. There's one problem that I found in the paper, but generally it's pretty good. This is interesting. So that these things are, because they're conductive, they're black. Okay, like if you see a conductive polymer, it's going to be black. It looks like metal, shiny. So obviously it's going to be hard to get a beam of light through it, right? So there's a huge absorption to this thing. And then it's also wavelength dependent. So this is about like visible light here. If you go down into, this is like, this is IR over here, I guess. And then basically in the visible range, it's got less absorption, but it's still basically black, right? You can't get light through it. It's because of that you get this huge effect. You have to, because with the Zim plot, you're going to increase concentration. This is the concentration series. And then you're going to extrapolate to zero concentration and zero Q. The Q part, you'll get RG. So you extrapolate to zero Q, and then you get this line. And that slope of that gives you RG. And you extrapolate to zero concentration. And then that line, the blue is zero concentration. And then you can get the chi parameter, the second Virial coefficient from that. Right, so the game in this is to extrapolate, so get your real data and then extrapolate down, because this function isn't the correct function, whatever it is. The Zim function gives it somewhere here. Maybe I missed it. The Zim function is somewhere here. This is, so it's 1 over the intensity, and then this is the Guinier's law part. And this is so these two equations alone, if you take theta 0, this equation is appropriate. And this equation is appropriate at concentration goes to 0. But just multiplying these two together like this doesn't give the appropriate answer. Right, so this function isn't correct except in extrapolation. Right, and you have to extrapolate it to 0 concentration and 0 Q for it to, and then you get these two equations. Right, so the 0 concentration one gives RG, the 0 angle one gives the second Virial coefficient, which is the chi 1/2 minus chi. And so anyway, the parent function though isn't a real function, it's just made up. Right, it wasn't derived. The Zim function is made up. So you can't exactly do a fit to data with this. Right, so but you can take data at different concentrations and different Q, and you can extrapolate back to 0 concentration, extrapolate back to 0 Q, and then take the slope, get RG squared of 3, and take the slope and get the second Virial coefficient, which is 1/2 minus chi. So you get the chi parameter. Right, so that's kind of the game here. What else? So that, I think there's mostly what's, let me see if I can find the quiz now. Here. Figure 1, explain the slopes. It's possible to measure the coil size. This brings up an interesting issue, right? So from this, he gives the race gyration. I digitized this data and I got almost the same race of gyration. So you can digitize those points and just fit Guinier's law to it, and you can get roughly the same race of gyration. The list here is about 20 nanometers, so 200 angstrom. Right, 200 angstrom. So if you take 2 pi over 200 angstrom, that gives you a Q, a Q value. And I did that in the answer sheet, so I'll just look at that. So whatever that is. I mean, it's like 0.02, I think, is what you end up with, 0.02 or 0.03. Excellent. Shows the race of gyration. So 2 pi over 200 is 0.03. 0.03. So if you go back to, so you should see a knee in the data, like you see a knee here. Okay, so this is 0.1, this is 0.0123 right here. That's 0.03 right here. Right? So you go up, and that data is for the chloroform samples, right? 1, 2, 3. You go up, like you should see a Guinier like right here. You should see this knee thing kind of right in here on this data, but it's not there. So I think nobody really picked up on that, but basically there's a discrepancy between the RG they report from light scattering and what they show for the neutron scattering. So it's kind of an issue. You could explain that. The only way I thought of to explain that is that there's a difference between in order to do neutron scattering, you have to deuterate. But if you just put a hydrocarbon in, and then you have a hydrocarbon with some chloroform, you get a little contrast because chlorine's got a little bit different neutron cross section compared to carbon and hydrogen. Basically, you'd see nothing. So you have to, in order to do that, you have to get rid of the H's in chloroform, replace them with D's. And D and H have the largest difference in neutron contrast of any elements. So that basically makes it, lights up your chain red or makes your solvent yellow or something. So it's a completely different color for neutrons. So basically that's the highest contrast you can get. So that's why they get pretty decent scattering data from this. Right, so you have to, even at low concentrations, right? So let's see, it doesn't give the concentration on that plot, but basically the concentration is low, right? So because it's implied, you have to be working with low concentration. It's like one mg per ml type thing. So anyway, so basically there's missing RG here, like it should be here, it isn't there. So that's because you saw it. So basically maybe the deuterated, there is a shift in the solubility with deuteration. That shouldn't affect the rates of gyration, but this kind of makes you think that these things might already be aggregated or something. There was something odd about between the RG that they measure and what you see in the neutron scattering that it disagrees. So I'm not sure. That's the one kind of flaw in this paper. Otherwise, I'm pretty sure they were happy to see the power 1. And then this is just the extrapolation of the power series for an exponential. And so this is good for anything. Like this is just Gunnier's law. They're not using actually any of the Polymer equations. So just Gunnier's law. That function is good for anything. So it can work for a rod. It can work for anything. Right, so that's fine to use that. And then the other part of that equation that they give is the Viral coefficient, and that also is good for anything. So the Zim equation isn't specific to polymers. It's mostly only used for polymers, but basically you can use it for rods. I mean, this is just Gunnier's law, so that's fine. And then this is the second Viral coefficient, that's generic. But there's no interpretation of it here until you say it's 1/2 minus chi. Then at that point you're using Gaussian chain to talk about it. So so basically this equation is fine for rods. There's no limitations. And then what else is in here? Did that. Figure 8 did that. Oh, and then there's another. I put in another paper that was this is a guy from Illinois that won the Dillon Medal, which is like a young researcher prize for APS, and he won it for this work on these free radical polymers, right? So you see the backbone here is polyethylene oxide, or PEG. Polyethylene PEG is PEG or PEO. Right? He calls it PTEO because T is a side group. So it's PEO with this side group. You see like these methyls sticking off of this kind of amine ring. I forget the name of that, but and it has a free radical oxygen here, right? So it's already stabilized because of the oxygen and nitrogen, and then it's further stabilized by having these protective groups around it. So these kind of give a steric shield to the free radical. Then the electron withdrawing of this thing also stabilizes the free radical. So this thing can be oxidized to a carbonyl. So you can put another bond in here by oxidizing it, put an electron in, get a double bond. Or you can reduce it and get this state, Then you can go also reduce it more and get a hydroxyl out of this. So this thing can go through transitions. Anyway, in this state, it's got a free electron. That electron is just free, you can leave, right? So if you can crowd enough of these groups around, cluster those groups, then you can get this conduction going to it, right? So this clustering of these things relies on annealing it. So you take that polymer, this polymer can be extruded and injection molded, you can cast a film, you can make a wire, right? So this it's just polyethylene oxide, it'll dissolve in water, right? So you can actually cast this from water if you want, right? And then the side group has this free electron, then you can make a conducting wire out of it, right? The conduction isn't great, like this number, Siemens per centimeter, is going to be 1,000 for copper, right? And it's 10 to the minus 3 here. So, but if this is a polymer, this is 10 to the minus 12, right? So normal PEO will be 10 to the minus 12. So you've raised it up to 9 orders conductivity. So it's into the range of conductive polymers, but it's not, you're not talking about something like copper, right? It's not something that can conduct that much. But you can use these for things like photovoltaics, and you can use them as collectors. You can put a dye in and collect the charge with this. And so it's used mostly in photovoltaics, actually. And you can make devices with this. This Budoris has been making medical devices with this for like doing sensing the pressure in your eye for glaucoma, things like that. But so it's kind of a big group, I think. I mean, it looks like they're doing a lot of different work. They're also doing membrane work in that group. But anyway, so this is kind of interesting to look at, to compare this. This is like the new conducting polymer, and the old conducting polymer is kind of what they were looking at. And the interesting thing in the old conducting polymer is a rigid chain and how you modify that structure. With the new conducting polymer, the interesting thing is how do you get these electrons to group up and make a conductive pathway? And maybe how do you improve this 10 to the minus 3 to be something like 1, like 1,000 times more conductivity, so you could actually do something with it. All right, so anyway, so nonetheless, like so this conducting polymer is a guy from UPenn who was previously from Case, won the Nobel Prize for this in a while ago, like in the late 90s, I guess. So there is a lot of interest. He won it in chemistry, but basically it was kind of a physics prize. It's a chemist that made those conducting polymers originally. So anyway, it's kind of an interesting area. It's a little bit off the beaten path of the polymer physics, but this P3HT is like a common polymer for photovoltaics. So they use a kind of a buckyball. They'll put a buckyball into the P3HT. So he's got this thing, P3HT, poly 3-hydroxy something. I don't remember what, but basically that's the most common connecting polymer for photovoltaics. And then that's used with a buckyball, like a fullerene charge collector. So you mix buckyballs in with that, they collect charge, and this conducting polymer carries the current away to the electrode. So that's kind of basically a photo cell, a polymer-based photocell, flexible photocell. Anyway, so that's that. Any questions on from the quiz? Or? So it's hard to jump back because I actually saw this tapes, but I didn't. So, but I think we're at this point, like to look at viscosity. So I'll start here anyway, even if it's not. So this is a Uber Hole viscometer. Hard to pronounce, but it's a pretty simple thing. So this part, like right here, you can't see it. I tried blowing this up and you can't see it no matter how much you blow it up. But through this path, like a little bit below the red line, the channel narrows down. And then there's a long, narrow capillary, and then it opens up down here before you get to this part. Right, so that length you have a capillary. So it's called capillary viscometry. Okay, and it's simple. So you take your polymers. First, you put the solvent in. right? And then you run it up and you get the solvent to go above this line with you use a bulb to push it in. And then you let it flow. So it's going to go slowly because it's going through this narrow capillary. And when it gets to this first red line, you start your stopwatch, you start counting. Then when it gets to the meniscus gets to the bottom red line, you stop the stopwatch. Then you have the time that it went through this, right? And then you put in maybe put in a high concentration solution, right? And then you do the same thing, and then you dilute it down with solvent and do it again, and then dilute it down with solvent and do it again. So you get a concentration series that way. So you mix it right in here. So you basically have two samples, then you put a bunch of solvent to dilute it down, right? And you get the time for each one. So that's kind of the game that you're playing with this machine, is just get the time. So it's simple to do. And then you're going to use Purcell's law. So, oops. Right, so you're gonna say the pressure head on this is constant, like mgh on this is going to be constant. Gravity is the same; it's about the same height. At least it's the same for every test through it. So basically, assume that delta p is the same, and then the length of the capillary is fixed, and the radius of the capillary is fixed, and the viscosity is changing, and Q is changing. So if you can measure, and Q is the volume per time, and the volume between A and B is fixed, right? So you just have the time. So you measured the time. So you have that Q goes with 1 over the viscosity, or has some constant divided by the viscosity. And then Q is also like some constant over time. So viscosity is proportional to time. Right. So if you don't care about the prefactor, this constant, just measuring the time gives you the viscosity. And the kind of, excuse me. So the kind of viscosities we're looking at are all some kind of specific or reduced viscosity, right? Because we know that if you measure the viscosity as a function of concentration, you're going to get to the solvent viscosity. And then some point it will take off and start shooting up, right? So this is usually a log-log plot. So that's why you can draw a straight line here. So you can't just use the time you used here. You need to use the viscosity minus the solvent viscosity. So you can get this curve, like the one that comes down here. And you expect to see a transition, so power 1 at the low end. Then you reach some point where you have entanglements, right? So you have kind of C entanglement, which originally is kind of considered the same thing as C star, the overlap. But they aren't the same. So CE actually doesn't equal C star. Right, but basically, for the original kind of thought about this, thought that CE was the same as C star. That was kind of the original idea. And then this goes to something like 3 here, maybe 3.2 slope. So you get entanglements, and the thing starts to go up much more rapidly. All right, so you're already doing this. So basically, this is generally reduced further. So you say that divided by this. So this is the specific viscosity. This is the reduced viscosity. Right, so you remove this because the solvent would have swamped out the whole curve, so you can get this part. And then you normalize it by the solvent viscosity. So you could write that as like this over that minus 1. That's another way to write that. This reduced viscosity. Right. So since time is proportional to viscosity, in this machine, you can just say that equals time minus the solvent time divided by the solvent time. So all you need is a time to get this reduced viscosity. Right. So that's kind of how this thing works. You might have already known that, but so anyway, what's of interest is how this thing, how this viscosity, like how does this viscosity change as you add colloids to it? Um, or I'll just see. This is milligrams per milliliter usually, which means so you have the solvent viscosity is enhanced by adding a colloid to it, and there's this intrinsic viscosity. Which isn't a viscosity at all, right? It doesn't have units of viscosity. It's not even, so this doesn't have units of viscosity. It has units of inverse concentration. So it's going to be milliliters per milligrams, right? Because the one has no units, so this has to have units of milliliters per milligram. And then the viscosity units come from the solvent viscosity to give you the solution viscosity, right? So, so this thing, so you can kind of see that these things have something to do with each other. So I can divide over here. I can take this divided by that. Then I can take the one and subtract it. And then I have like this guy. So this thing is the reduced viscosity equals this intrinsic viscosity times the concentration. Right? So it kind of makes sense. Then you can just divide by concentration, get the intrinsic viscosity. But there's a problem with that because this viscosity changes with concentration. Right? In other words, this number changes with concentration, but because it's going to be linear down here, right? Then if you divide by concentration, so you take this has to be done in the dilute limit. So the limit of C goes to 0 because it's going to be linear in this region. So you can pull out the C and then you can get the intrinsic as a fixed number. Right. So why is it linear here? It's because as you add concentration, so say this is for colloids. So if you just add, like if you have a couple, 3 spheres, and I make it like 6 spheres, then that doubles the viscosity. And so it's just a concentration effect. The one is just how much you put in. As you increase the concentration, the viscosity increases, and it's proportional. That works up until these spheres have some kind of interaction, like if they're charged or if they're polymers and they entangle or whatever other kind of interaction you can imagine. It could be hydrogen bonding, there could be van der Waals interactions. There could be any kind of interaction. Once you have interactions, then this thing is going to go up steeper. That's why you have to go to the dilute limits. This looks a lot like the ideal gas law. Like you're looking for a point where you can consider these colloids, which are generally drawn as a little sphere, where they're dilute. So basically you're assuming that the colloids can pass through each other without any kind of effect. Right, so that's the same assumption as the ideal gas law. So this thing is kind of like this intrinsic viscosity, something like an ideal gas number, except the viscosity is a dynamic number. So it's like taking the same approach as ideal gas, but doing it for something that's dynamic. So ideal gas is for equilibrium, right? But this is dynamic. So it's kind of like a mixed bag of things here. That's why this looks like C star. So anyway, what is this intrinsic? It's like how much volume does your object take when you put it in? So it's going to be like per gram, right? So it's going to be the molecular weight. So it's going to be in volume per gram. So it's going to be the molecular weight. It's going to be the volume of an object. could be a sphere, so you can calculate this for a sphere, or it could be a polymer chain. So you can calculate this for a polymer chain. And so this is kind of an interesting number. So if it's a sphere, this is a fixed number, and this thing's 2.5. And Einstein, because in a 3D object, this number is a fixed number. So we'll see how that works here. Right? And again, I don't remember if I did this already, but so we have the intrinsic viscosity equals the volume over the molecular weight. And then we can say that the size to the df gives you the mass. Right? So if you want to get size, you take, so we can substitute in size to the df here if we want. And this volume is size cubed, so I'm just doing scaling. So I'm going to get size cubed minus df out of this. That's one way to look at this. Or you could say that the mass, you could say that R is molecular weight to the 1 by df. And then we have R cubed, so you'd have, or then you could say R cubed, so it would be 3 minus, so it also is like molecular weight to the 3 from RG, from 3 by df minus, so R is molecular weight to 1 by df, it would be 3 by df minus df minus, minus 1, because it's molecular weight. Okay. Right? So you can either write it in terms of size or in terms of molecular weight, this guy. So generally, if you're doing polymers, you want to know what the molecular weight is. Not really, this size, by the way, is the hydrodynamic size. So it's whatever size it appears to have in a fluid. In other words, if you have, say you have a rod and say it flows that way, that size is going to be the diameter. Right? If you have a sphere, it's going to be the radius. If you have a polymer chain, it's something between the radius and the diameter, depending on how the solvent flows through it. So the hydrodynamics. Right? So it's called the hydrodynamic radius because the solvent could fully drain out of the chain, then it's going to be kind of the diameter, or it could be non-draining, so that then it acts like a sphere, and then it's going to be like a sphere. Depending on how the solvent attaches to the polymer, you're going to get some between these two limits of what this number is RH. Right, so hydrodynamics governs this thing. And for polymers, it becomes kind of a complicated phenomenon. For spheres, it's not that big of a deal. Right, so for a sphere, so if you have df is, say df is 3 for a sphere, then this 3 minus 3 is 0. So something to 0 is 1. So it's a fixed number, 2.5. The same here. If df is 3, 3 by 3 is 1. 1 minus 1, 0. So it doesn't depend on the mass. So this thing doesn't depend on mass for a 3D object. It's just 2.5 for spheres, and it's some other constant for other shapes. And Einstein calculated this. That's called the Einstein equation. You go like this equals 1 plus 2.5 times the concentration. And that's the Einstein equation. So you'll see this 2.5 floating up in a variety of places. And people will talk about the modulus of the composite. So you have a composite with some kind of carbon black in it, and you say that you have the modulus of the composite is going to be the modulus of whatever it is that the polymer, times 1 plus 2.5 times the concentration. That's called the Guth-Gold equation. So they've taken something like viscosity and they'd said viscosity is like modulus except with time, right? Because you have stress is a strain rate times viscosity, and then you have stress, even though it's usually XX and XY, is the strain times the modulus. So this strain rate is the change in strain with respect to time. So this thing is like time. So it has another time in it. It's basically going to be like modulus time. right? That gives where the time makes stress. So the viscosity is going to be something like modulus time. So if you have modulus, we say modulus follows the same kind of thing. So that's a common equation. Then people will like add in other terms to this, like c squared, whatever, the power series into this, and put in whatever. Beth Gold had some number like 12 here, I think. Right. So this is for rubbers, like reinforcing rubbers. What's the modulus of a rubber with carbon black in it? So they just steal this Einstein idea, pop it through. So why this is a fixed number is because what this thing actually does is just displace the fluid. So if you have your stuff in the fluid, right, and you get the viscosity, say you could settle out all those particles and just that stuff doesn't flow. Oops. The stuff that you settle out doesn't flow. So you just have decreased the volume of your fluid. That's why the viscosity goes up. So like the apparent viscosity goes up because you've displaced fluids. This is a displacement law. It's just saying whatever you put in as a solid object, it doesn't matter if it's nanoparticles or if it's bricks, it'll settle out into a certain volume. I've extracted that volume. That's why I get a higher viscosity with the composite. This is a pretty simple idea, like that you're just going to have this displacement law to get rid of some of the fluid. That just boosts it's the same thing here. You get a higher modulus because you've displaced with an infinite modulus material, like something that doesn't move. And that makes your modulus boosts your polymer modulus because you're basically you've taken out some of the volume, right? So, but if you have a polymer, this thing scales with kind of the density. So the density changes with the mass of a polymer. If it's small, it's got a high density. If it's big, it's got a lower density. And the bigger it gets, the density gets lower and lower, right? So because the density drops, its displacement volume drops. And because the displacement volume drops, this thing's dependent on the molecular weight or the size, the hydrodynamic size. And again, that changes with the interactions with the fluid. And so that's like generally what's going on. So this this business of the intrinsic viscosity goes with K times molecular weight to the A. That's called the Mark-Hoink equation. And this is Herman Mark from Brooklyn Polytech, kind of 1960s. Right, so he was a German that came to the US, I think escaped the war, like Debye and some others, Einstein, and then Brooklyn Polytech, I think it was Jewish, that was like a Jewish part of New York, and this was the top science school in the United States at the time. It isn't anymore, it still exists, so it's still a good place, but basically MIT took over from Brooklyn Polytech in World War II. Right. But Brooklyn Polytech at the time was the top place in the US for science. And Mark was there and he did this business. So what do you get for A? So A, if you do it in terms of molecular weight, we have molecular weight to the 3 by dF minus 1. So you can go through like a rod. So dF is 1, and this thing is 2. Right? 3 by 1 is 3, minus 1 is 2. So we have the A parameter. Mark-Hoink A. Right. And then you have expanded coil. So dF is we'll say it's 5/3. It's really 0.588 or 1 over 0.588, 1.7. But anyway, for that case, so we have 9/5 minus 5/5 gives 4/5, which is 0.8, right? 0.8. If you use 1.7, let's see, I don't know what that number is, but and it's 0.76, right? So you can put a thing like 0.76 is kind of what maybe that is. Then if you say Gaussian, df is 2. So 3 by 2 is 1.5 minus 1 is 0.5. Right? You see this is going down as your dimension goes up. So we go to 0. So we go to 3D, that's 0. Because 3 by 3 is 1 minus 1, 0. Right? So 3D sphere. So those are kind of your options, like a menu, right? You can look in the Polymer handbook for those numbers. I didn't do that. I should have done that. Maybe I can do that quickly. Let me see how this is going here. If that would just show some parameters, but they're going to be kind of in that range, right? If you have something like cellulose, oh, there's a table down there. I should have gone to that. Let's see, is that table in here? No. Let me go back. There's a table down right here. This looks like what I want. It's like a bunch of numbers. Anyway, if you look under cellulose, you get something close to 2 because it's a rigid structure like cellulose acetate. And then I don't have the Polymer handbook handy right here. And then as you look to like, you'll get a range of these numbers, you know, so it depends on kind of how this thing goes. So it'll be between 0.5 and 2, the number for this Markov coefficient. And the advantage is this measurement is a really simple, like this is such a simple measurement, and you can get the molecular weight out of it with not many assumptions, right? So basically, you can get, so if you're doing synthetic chemistry, you can do this pretty easily. You know, you can measure out your mass, you measure out your volume, then just get your time to flow through this, and from that you can get this thing, you can get this number in grams per mole if you have this A parameter. So if you know what you're making, it's been already done, then you can just use this as a secondary standard and get your molecular weight. That's pretty simple to do. It's cheap. You need a glass blower to make one of these, and that's it. Right. So basically, this could be done in 1950, and it was. It was done. It's still done today. Like a lot of chemists will use this as a way to get a molecular weight. All right. So that's getting this number, this hydrodynamic radius. Right. So it's this thing. So there's a book. I found a book that's pretty good on this stuff. I put it up on the web page. This guy is at, it's 2 people that wrote this book. Let's see. Yeah, here, colloidal rheology. This kind of goes through a lot of other things that are pretty useful in a pretty simple way. Let's see. I guess I don't have it up yet. It should be there, but it looks like it didn't get there somehow. Anyway, I have this over here somewhere. But it's probably worth taking a look at that if you get into desperation to figure something out. It might be handy to take a glance at it. If this opens, yeah, colloidal rheology. So it's like colloidal suspension rheology. This guy Wagner is at Delaware. He's a kind of a hotshot character. He's pretty smart. And he does scattering and rheology. So he's trained as a rheologist. Anyway, it goes through kind of basically the rheology ideas, and it gets does stuff on intrinsic viscosity and kind of how, basically it's worth taking a look at this, flip through it and see what you think. You know, it can answer some questions, I think, about this colloidal stuff. One thing, he goes through the charged colloids part and seems to do make it pretty simple. You know, he talks about the hydrodynamic effect and kind of how this solvent sticks to things. And so it's actually pretty good. There you can see this is the Einstein equation, 1 plus 2.5 phi, and then they add in, just do a power series on it, add in other terms, right? So it could be, if it was modulus, that could be the Guth-Gold equation for composites. Anyway, so that book might be worth looking at. So there's a guy that actually did a lot of work on this at Case, who's, I don't know if he's still alive, but he was in the 90s, you know, and he was kind of the founder of the Polymer program at Case. And one of the main things he did was this intrinsic viscosity measurements. And then Jameson is a guy who does dynamic light scattering and some other stuff, who's at Case also and probably retired by now. But he followed in the footsteps of this guy, Simha. So Simha has an equation, the Simha equation for intrinsic viscosity. Anyway, he kind of founded a lot of the stuff about different shape colloids, intrinsic viscosity and charges, and how this thing morphed into more complicated than just this simple Mark-Hoek business, right? So the idea is like the first thing you can do with intrinsic viscosity is like take this into a power series, right? So you can, I mean, this is a classic engineering thing to do, is just you have this linear dependence and say, well, it's not following a linear dependence. So I have some problems, so I'm going to just make a Taylor series expansion of it. These things would be the derivatives of viscosity with respect to composition, like the second, third, fourth derivative. And then basically find these constants, and then I can construct more complicated shapes to this business. Okay, so what's happening when you get a more complicated shape? So you're assuming that the structure doesn't change with concentration, right? So you're assuming you have a fixed let's see, where's the thing here? You have a fixed, kind of a fixed structure, or with shear rate, right? So it's basically assuming you have some structure, say it's a polymer. Then you're saying, like, as I add more concentration in, that structure remains the same. So because you're talking about the displaced volume of this thing, like what is the volume actually? So you know the mass, that's a fixed number, but the volume, like how does the volume change with concentration, right? The hydrodynamic volume. So you have it's in a shear field, right? And you have solvent molecules in this stuck to it somehow. Some of them are stuck, some are flowing, some can flow out, some are bound. Some extent of the solvents are stuck. So the size of this is going to depend on how the combination of the shear field and then the interactions of the solvent with the chain, how those change, right? So say you have something like a polyelectrolyte. So if you say you put some charges on this guy, and they have some counter ions floating around. Okay, so the more concentration you put in, the bigger the counter ion concentration. So that lowers the screening length, which means the charge effect disappears. So you could start with a polyelectrolyte that's got a big hydrodynamic volume. And then as you increase the concentration due to the by screening of the charges, that volume drops, right? Because all of a sudden the solvent can drain out because it doesn't have a charge anymore. The charge, it still has a charge, but it can't be felt. Right, so you can get pretty complicated behavior out of this simple thing for charge systems and also for others. So I'll continue on with this next time. Okay, so anyway, that's about it. If there's no questions. All right, see you guys later.